Okay, welcome back to Let's Do Logic in Type Theory. So far we have seen that things seem to work out fine for implication, conjunction, true and false, and we next would like to do disjunction. So we ask the same question again: what does it mean to prove A or B? And we think a little bit and we say that, well, it means that we should prove A or we should prove B. Right. But what does that sound like? Well, that sounds a lot like the disjoint union type that we have seen before, right? Which you can see in data sum. So let's go hunting again. Here we go. So here we see that to prove A or B, we could either give a proof of A or we can give a proof of B. And these two constructors are called ing1 or ing2 or inject. Right, and you type this thing with this \u plus, because there's a little plus in the middle of the u here. Okay, so we do make this identification. We say that OR is represented by the disjoint union. So let's do an example and see if we can prove that if A or B is true, then B or A is true. Okay, and how do we prove this? Well, we write the program because that's what we do. So I'm going to call this X, and this is my goal. And now I can pattern match on my X, and I see that, well, my proof of A or B is either a proof of A or it's a proof of B, because ing1 is the first injection, ing2 is the second injection. So I'm going to rename this XA and this YB, because it makes it a bit clearer for me. It doesn't matter for Agda. And then I can see, right, so here I have to give a B or A, and I have an A. So the obvious thing to do is to use the second injection, right? So to get this little subscript 2, I do \_ and 2, by the way. Okay, so I do the second projection of A, which goes into something plus A, and that's what I want. And similarly here, I want a B or A, and I have a B, so I can use the first injection to do that. Right. And again, to get this subscript 1, you might have already figured it out, but it's \_ 1. Okay, so we can also represent disjunction. That's good. What about negation? So what is a proof of not A? Well, it should be a proof that a method to show that all proofs of A are impossible, which, if you put it differently, is a function from A to bottom, right? So if you give me a proof of A, then I will give you a proof of bottom of the empty type. So that's impossible. So we can make this identification. We say that not A is the same as A implies bottom. Right, so let's try this. So here's a statement which says that true implies false. That hopefully should not be true, so I've put a negation on the outside of it, and then we can try to prove it. So okay, here the goal is this, but I can normalize the goal. So I do Control-C, Control-U, Control-U, Control-C, Control comma, and it has written out what the goal is using this definition of negation. Right, so we see that again we have to produce a function into the empty type. So I'm going to call this X. Okay, and now we see that we have to produce something in the empty type. Well, that's a bit scary because we just said that the empty type has no constructors, right? But maybe this X is also impossible, so we can blame the X. So let's see what the X says. Well, the X gives us a way to construct something in the empty type if only we give it something. So we do x applied to question mark. Okay, and now we are done if we can fill in this goal, and this goal asks for an element of the unit type, but we do know an element tt, right? Or again, if we are lazy, well, I can do that. Again, if we are lazy, we could also say you figured out what the element of the unit type is, and I'm just clever enough to do so. Maybe tt is clearer here. Okay, so we managed to prove that it's not the case that true implies false. That's also reassuring. And here finally is another example of negation, which is the principle of explosion, which says that if A is true and if not A is true, then everything follows from this. Right. So let's see if we can prove this. So here I've already introduced the A and the proof of A and the proof of not A on the left here. So I have to give an element of B. And what do I have? Well, I have these two things. So in particular, it looks very tempting to apply this proof to this proof, right? So if I do that, not A apply to A, Control C, Control full stop to see what I have, then I see that I have something in the empty type, but I know that's impossible. And we proved earlier that if you have something in the empty type, then you have something in any type. So I can just apply x5 to this. And that gives me something in some B, which hasn't inferred yet, but it's going to do it if I give it, because then it's going to unify what it has with what it wants. So I can load that. So we can also prove the principle of explosion in the logic of Agra, which is reassuring.